Welcome to this video entitled Accuracy and Errors. The question we're handling in this video is how can we make our experimental results as accurate as possible. And it's the first in a series of 3 videos on accuracy, errors and uncertainties. So if you'd like to go into uncertainties, then please click the appropriate link now. And if you're interested instead in looking at a worked example of how you can calculate uncertainties and relating them to errors, then there's another video that you can click the link for now. But this video is looking really at the theoretical basis for accuracy and errors in experiments. Those are the learning objectives. Let's begin. So first off, the concept of accuracy. So I wonder if you want to pause the video and think about this question. Which of these measurements, A and B, is more accurate? Well, hopefully you realise that A was the more accurate, and hopefully you had an idea of why, being that actually A is far closer to the true value. So if we look at the difference between B and the true value, we're about 0.9 centimetres cubed away, whereas A is only 0.2 centimetres away. So the closer you are to the true value, the more accurate your measurement is. And indeed, this is the definition of accuracy: the closeness of agreement between a test result and the true value. So in our experiments, if we're going to do a good experiment, we want to have high accuracy. We want to be close to the supposed true value. Now, accuracy is closely linked to the concept of error. And the error of a measurement is simply the difference between an individual measurement and the true value. And we can define 2 types of error. There's the absolute error, which has the same units as the measurement. And that's just simply defined as the measured value minus the true value. And notice the sum. And notice the way the subtraction goes. Measured minus true. So for A, we'd be doing 10.2, take away 10, which comes out to be 0.2 centimetres cubed. Whereas for B, we would be doing 9.1, subtract 10, and the answer to that one would be minus 0.9 centimetres cubed. So notice that it carries a sign with it, and if you've got a negative sign, that means your value is too small, and if you've got a positive sign, which often you'd leave out, that means your value is too big. Now, the absolute error is not as useful as expressing it as a percentage of the true value. So to find the percentage error, we simply do the measured value minus the true value, and we express that as a percentage of the true value. So notice that that is in the denominator here. So if we want to work that out here, then for the case of A, we would say that the percentage error is going to be the measured value minus the true value. Now that's just the absolute uncertainty. 0.2 divide by the true value, which is 10, and times 100, which comes out as 2%. And again, it would be plus 2%. And in the case of B, you might want to pause the video and try this. We've got minus 0.9. We're going to divide that by our true value of 10 and times 100, and the result comes out at minus 9%. And the percentage uncertainty is really useful because depending on the size of the true value, a particular absolute error might be good or bad. And really, a percentage gives you a better idea of how accurate your experiment is. So just in summary, in our experiments we want high accuracy, and what that means is we want low error. And really we're looking at the percentage error there. 5% is good. Well, we're going to see in subsequent videos really what good is. It depends on the situation that you're in, but depending on the field you're in, 5%, 10% would be a reasonable error. The final thing we're going to look at is 2 different types of error, and the first here is random error. And random errors arise from limitations in correctly functioning measuring equipment. So every time you take a measurement, you get a random error. And the effects of random errors are shown by the dartboard here. So this is equivalent to a dart player who's playing, and they are missing by different amounts every time. And then beneath the dartboard we see if the target was the green arrow, then the red dots indicate that sometimes the value you score is too low and sometimes it's too high. So in summary, for random errors, they're unpredictable in size. Some results are too high, others are too low. However, if you take the mean, which is given by this blue arrow here, then the mean of all these the mean of all these different test results turns out to actually be pretty close to the true value. And so you can always overcome random errors by taking a mean. Now, random errors are always known about in the sense that they always arise. There's no time you take a measurement where there isn't going to be a random error. And so in that sense, they're unavoidable. So in our experiment, we want to try to minimize random errors. And the way we're going to do that is by working carefully, using better equipment, because that's going to have a smaller size of random error, and also taking the mean, which we've seen here, actually gets us closer to the true value. Now, much more serious is so-called systematic errors. So this would be an example of a dart player who has a systematic error. They're always missing by a similar amount each time, and they're always missing in the same direction each time. So if we look at the red dots here, the green arrow is the true value. They're going always to beneath the true value or to the left of it. And systematic errors are sometimes known as bias. Systematic errors have a predictable size or at least a predictable direction. You can always say it's going to be either too high or too low. Now, the problem with systematic errors is that even if you take a mean, the mean ends up far away from the true value. Now, often the other problem with systematic errors is that you often don't really know about them. If you have a systematic error or not, you won't be able to tell by doing repeats, because you could have your repeat values very close together. In other words, the experiment could be very precise, but still you've got a systematic error. But the good news about systematic errors is they're often avoidable. And they arise from problems with the procedure that you use or with using faulty measuring equipment. And so you can minimize systematic errors by careful experimental design and also by calibrating equipment. In other words, making sure that when the equipment says it measures, say, 5 grams, it's definitely measuring 5 grams. So you should always regularly calibrate your equipment to minimize systematic errors. And one final thing just to note is sometimes systematic errors are known as procedural errors. And that's basically saying that you have designed your experiment badly, and therefore the procedure that you use is causing problems or causing systematic errors to arise. So those are the different types of error. And remember, our aim is to try to minimize both so that we have the lowest possible error and hence the highest accuracy in our experiments.